CV. So he's graduated from the Faculty of Mechanical Engineering, University of Belgrade in '78, and performed his PhD in '88. Since 2001, he's full professor at the Faculty of Mechanical Engineering in Belgrade. His main topics of research is engineering materials, welding, numerical methods, mechanics, and structural integrity. He has been published more than 120 papers. Today, Professor Sedmak is going to talk about the plastic fracture mechanics in high-strength flow alloy steels, the integral approach, and micromechanical modeling. This session is also dedicated to GRI's 18th birthday. So, welcome to the Summer School, Professor Sedmak.
Thank you, Luis. You can hear me, I guess. Okay. My name is Aleksandar Sedmak. I'm coming from Belgrade, Serbia. It's my great pleasure to be here. I'm so happy that this conference is finally going on. It should have happened 2 years ago, and in that year, James Rice celebrated his 80th birthday. So this dedication is now 2 years off the record, but anyhow, I still believe it should be dedicated to him, since in all these topics he was the first and the most important person in the world to establish elastic plastic fracture mechanics, J-integral, and micromechanical modeling. My lecture will have 3 parts. In the first part, kind of introduction to elastic plastic fracture mechanics. 15 minutes, as you can see, we already spent that. I will try to make it up. Then I will talk about J-integral applications, and finally about micromechanical modeling. But still, I want to say a few words about James Rice. 4 years ago, at the previous conference, he was not only the introductory lecturer, as shown here, but also he had probably the best ever lecture in summer schools. It was on the occasion of the 50th anniversary of J-integral introduction to fracture mechanics. Because, as you probably know, it was 1968 when the famous and probably the most cited paper of fracture mechanics was published. It was on J-integral. There are 2 links here which I wanted to show briefly, but we don't have Wi-Fi here, which is probably good for your attention. You can, of course, check this later if you're interested. You can see his lecture during the summer school almost 4 years ago. And you can also see video clip that we made on 3rd of December 2020 when we had online seminar dedicated to his 80th birthday on this real day of his birthday. He was present as well on the screen, of course, and it was very, very nice event. Our ex and the best ever president, Leslie Benzils, was also participating. Our actual president, Francesco Guglielmo, was there, and there are a couple of lectures dedicated to Jim Rice. It's really impossible to explain all deeds that he made during his relatively short career in this field, because he switched to some other topics later on, but in about 10 years he established all disciplines in fracture mechanics as we know them today. Okay, so now lecture, and now I will sit because I have a slight problem when I stand too long. Just let me say that you can ask questions, of course, except professors who are present here. They are not allowed to ask questions. So let us start with limits of linear elastic fracture mechanics. that is probably the best way to get to the topic of elastic plastic fracture mechanics. So when large amounts, relatively large amounts of plasticity occur, the stress intensity factor is no longer a valid parameter. We need something else. We can try with plastic zone calculations, and we can also try to do something with these curves, low displacement, which are in that case non-linear. You can see them here, but you can't see there. Well, sorry. It's not there. Okay, from time to time. So this is. Oh, the other. Okay, thank you. So this is the nonlinear, as you can see, and here we have this plastic zone, which is small, and inelastic fracture mechanics is valid. I mean, K is valid, but in this K, with the large plastic zone, which is already as large as K zone, we need something else. How was my good? Carol. SOS. Okay, sorry for this. Now, for plastic zone corrections, there are two famous formulas depending on plane stress versus plane strain. You can see also on the sketch to the right the difference between them. This is plane stress, this is plane strain. And yet another way to incorporate somehow at least plasticity is to use failure analysis diagrams, because here we have representative of brittle fracture on the ordinate, and on the axis we have representative of stress, and that stress can go up to the plasticity, above the plasticity, and that is how we get out of the limits of linear elastics. So, in discussion about linear elastic fracture mechanics limits long time ago, there was a reasoning which is quite logical, that if material toughness is so high, if plasticity is present in a relatively large amount, that cannot be measured anymore like K, then we don't have to worry about fracture toughness at all. But that's not the case. We still need to evaluate fracture mechanics parameters. That was first argued by nuclear power plants, and later on with application of some new materials like micro alloy steels. They have a lot of plasticity, but still, in some cases, they can be critical. Just to mention one of my favorite topics, behavior of welded joints. So we really need these elastic plastic parameters. And those are mostly mostly used are two of them, J integral as defined by J Rice, and also crack tip opening displacement. It was developed about the same time in England, and it was very often used in weldments, petrochemical industry, and generally speaking, they are maybe equally used. There were a strong discussion for decades that followed after the 60s, which parameter is better and so on. But the final decision, in a way, to say is that they are about the two sides of the same approach, and they were later on related, correlated, although with not exact equation. You can see that there is a coefficient m which depends on plane stress versus plane strain conditions, so it's not exactly from continuum mechanics, but a bit more empirical. Well, this is so because crack tip opening displacement is mostly empirical parameter, whereas J is very well sound based in continuum mechanics. Anyhow, crack tip opening displacement is a valid parameter, it works, and as people say, we use and not excuse it, regardless of the fact that we don't have a theory background. Also, some other parameters like crack tip opening displacement 5, which means that it is measured 5 millimeters above or below the crack tip, as suggested by Dr. Schwalbe. They are quite useful, and they are maybe nowadays quite attractive because of new options for measurement like digital image correlation. It was quite difficult to measure such a parameter with 10 gauges, but nowadays it is a relatively simple task. I hope I'm in the right slide. I'm really a bit lost with this, but it seems to be. So J integral as defined by Jim Rice in 1968. You can see it here. It is path independent integral. It has some displacement, strain, and strain energy parameters, quantities that should be integrated. You can see this traction T as well, which is there. And you can see, I guess, at once that it's not easy to use such a definition for experimental measurement. If we compare it with crack tip opening displacement, it is just the geometry, and you can measure it easily. In this case, you will see how actually it was measured, but it's definitely not directly seen from this equation. This equation comes from the continuum mechanics principles, and I will show that later on. Except the first fact that this is path independent integral, we should emphasize two other important facts. First one is to the right on the screen. This is energy rate definition, which is, I think, quite clear here. You can see that for two identical voltages, just slightly different size, there is an area on a wall displacement diagram which is equal to J times increment of crack length. So at the bottom you can see that the J is theoretically soundly correlated with the total energy that means it is energy release rate. And that means it is a valid fracture mechanics parameter. But to experimentally evaluate its value, to measure it, it is a bit different story. One of the first attempts, and later on used quite often, and it was by Landis and Billy, is to measure area on the diagram of displacement and to divide J into elastic and plastic part, and then to express elastic part to K factor and to correlate plastic part with this area. Now this is the second, what was important about J integral, and the third one is that it is a parameter characterizing plastic crafting fields. Those are famous, as we call them, HRR fields, that is due to Hutchinson, Roosevelt, and Rice. And in the next slide, I will okay. From time to time, I guess. So, already mentioned crafting fluid characterization. That was in the same year when J integral was introduced. Then, just 2 years later, Billy and Landis first measured J integral, and that was the first experimental fracture toughness measurement, but to elastic plastic parameter. So that led to some early J standards. Later on, Joyce has introduced a relatively simple J testing technique, and then we introduced master curve. And then, of course, what they haven't mentioned so far is computational fracture mechanics, and that also started in 1971, also due to Jim Rice and his students. That was the time where the singular elements were introduced. Finally, one very interesting experimental technique is direct measurement of J integral, which I will mention later, introduced by Dave Rice. Now, crack tip opening displacement, I think you all know what these slides are about. You can see this geometrically defined parameter. Of course, from the very basic fact that we can define it in slightly different ways, we can conclude that it is not a perfect parameter, but anyhow, as I told you, use and don't excuse. Just know about its limits. So to evaluate this ductile fracture toughness, we need also to measure so-called resistant curve. The end of the lecture. To do so, because this is now elastic behavior, so it's not just an event, it is a series of events, start with initiation of crack and then propagation of crack. To some point it is stable propagation and then it becomes unstable. So this is why we need the whole curve, and this is what was also introduced in these years that were already mentioned. And just to emphasize that Billy and Landis' first efforts were so-called multi-specimen technique, which means that they needed at least 4 specimens to get this curve, but later on, also due to some research of Rice Paris, which is another fracture mechanics legend, and their co-workers, their simple specimen technique was introduced, which is nowadays exclusively used by Billy. So, what I just described is ductile fracture process. You can see here 4 steps. Without the load, there is just a sharp crack, then crack blunts, and then initiation of crack growth is step 3, and its further growth, ductal crack growth is step 4. These steps are also marked here on the curve load displacement, and finally this right bottom curve is JR, so-called JR curve. This is J versus crack extension, and you can see also steps marked there. This difference between single and multiple specimen is shown here. You can see to the left at the bottom those at least 4 points needed for multiple specimen. That means at least 4 specimens, which is really not practical. But then once Paris and Rice noticed that elastic slopes can be used as so-called unloading compliance technique to actually measure or monitor crater growth, then single specimen technique was all set to go. So this is one of recorded J curve, and from that curve we can extract one of the most important parameters. This is J1C, that is fracture toughness, which can be correlated with K1C, and there is a procedure how one should do that. I'm now trying to run faster because we lost a bit of time. And the same story is about crack tip opening displacement. There is this critical value at the onset of unstable fracture. Then without crack growth, then this delta U is with stable crack growth. Delta I is at the initiation, and M is at the maximum growth plateau. These more or less follow the same story as J integral. So these facts all these facts we should know, so that we know when we are transferring our test results to the real component what we are actually doing. And I think that is one of the last slides in this first part. As I mentioned, standards followed very closely even those first attempts in 1971 by Landis and Billy, but later on there were standards on CPOD and then standard K, and finally people realized that all of them can be combined in one standard, so nowadays we use dominantly this AST and E1820, which cover even classical linear elastic fracture toughness K1C. Now, just a brief mention at the end about other material behavior. Fatigue was also on the agenda to try with the delta J, but that has not become popular. Maybe it still needs to be done. Environmentally enhanced cracking, the stress corrosion cracking, stuff like that was not characterized by nonlinear parameters, but creep was indeed characterized by nonlinear FM. So-called stationary creep can be very well described by completely analogous procedure as J integral is. So I think now that we completed the first part, and those couple of summaries are already emphasized. So let us go to the next chapter, and with that I need help in trying to speed. So how do I switch to the other? So the second part of my talk is about the J integral and practical applications, which will cover J integral as the conservation law, J integral for multi-material body, that means elements in this case, then direct measurement of J integral, and finally application of JR curves versus graph driving forces with one short case study. This is just to scare you. I do not go into details, don't worry. J integral as a conservation law derives its fundamentals from tensor calculus, continuum mechanics, conservation laws. You can see here many simply written but complicated equations which are in tensor form. But the point here is at the bottom is Jk, which is closed path integral and also transformed to the area integral, becomes Rice's J integral if we put k to be 1, if we consider just a graph along axis 1, which is abscissa, which is x-axis. After we do that, we can also prove that it is path independent integral. Once again, there are a couple of equations written in a simple form, but not as simple as they look like, so we are not going into details. Just I want you to see what is behind the story of J integral as a conservation law. So this scheme at the bottom to the right, with C1 and C2 as two paths around the graph tip, we can prove that J integral has the same value for both of them, because on the parts C minus C plus, J integral is actually 0. This is of course a path which contains or encompasses crack and crack tip. Otherwise, if there is no crack on this path of J integral, its value is 0. And that also enables physical interpretation as energy release rate, as you can see here. And finally, just to remind you that elastic crack tip fields are characterized by J, as you can see in these equations correlating stress and strain with their fields. So the first actually measurement was based on these sketches shown here. Let's say 4 different specimens, and differences in the measured values enabled calculation, experimental evaluation, of J integral. Of course, also this can be used for calculation as well. And now, after this short introduction to continuum mechanics aspects, let us see how we apply J in the case when one of the fundamental assumptions is violated. One of the fundamental assumptions of path independence. And that fundamental assumption is that material is homogeneous, and at least in the direction of crack. That is because there was a derivative, but let's not go into details. Let us now focus on these practical aspects. So here we have a multi-material body. This is a welded joint, and this analysis was done decades ago because we needed to check how big is an error if we directly measure J integral. So the point here is that if we measure J integral around the path gamma, which goes all over this specimen, we are crossing different materials. By crossing different materials, we are violating this fundamental assumption, and we are making some kind of error. So let me briefly explain. Welded joint, as presented here, consists of weld metal, at least two different heat effective zones, subzones, that is to say. This one we call coarse grain, and this one we call fine grain heat effective zone, and then of course comes base metal. At least these four regions have different properties, but with common steels, and I'm today talking about steels mostly, these differences are not a big deal. You will see later on, we pick up to about 10%, maybe 20% of difference in properties, and then maybe 10% of an error. Nevertheless, if we would have considered welded joint of ferrite and austenite steel, then we would have a much bigger difference. Now, in our practical experience, we didn't face that problem, so you will see that my conclusion will be that although theoretically big deal, practically this is not big deal. But let's see. First of all, if we have just the integral of part gamma 1, which is this one, which is inside weld metal, then it is path independent, and that value should be okay. But as I just said, in practical terms, what we can measure and what is measured in direct integral technique are strains along outer surfaces, because we can't get into the depth, and these strains will enable us to evaluate the integral, but that part is not path independent. Gamma 1 is, gamma is not. Now we need to correlate them, and you can see that this J integral along the whole gamma path needs to be corrected with all these line integrals around these interfaces, and then it will get back its path independency property, and then it will be once again valid fracture mechanics parameter. So, to prove that we made some calculations, these results are 40 years old, so don't expect something spectacular in color as nowadays, and I'm intentionally showing you how it was done decades ago, because what we did at that time is fully understanding of how to evaluate any fracture mechanics parameter, and in this case J integral. Because there is a bit of danger nowadays if somebody does not know what is behind the story and just uses all these commercially available finite element codes. There is a big danger of getting what we called decades ago DIGO, garbage in, garbage out. If input data is not good, your structure will fail and you will not notice. So this is why it's still good to know what is behind the story and how you deal with something that is not exactly theoretically sound. So here we made this calculation, and of course, according to the previously shown slide, we can combine these integrals along paths which encompass crack tip, like this one, and those line integrals which will actually show us how big is the contribution of the interface, how big is error that we make if we neglect it. Now, to be sure about that error, we need exact value, well, what we can get from segmentation analysis, which is close to exact, of course. And for that, we used 6 paths which are inside weld metal. They are shown here and they will be shown later as well. You can see here. So these 6 paths are in these 3 layers of elements which were positioned at the graph tip. Those were the times where we prepared our input data manually. And here you can see now J integral along paths 1, 2, and 3, which crosses over interfaces, so their values are a bit different. For example, in this row you can see 247, 225, and then once again 247. These 2 are really almost the same, but that's coincidental. We should focus on this difference, which is about 10%. But then if we combine these integrals with line integrals, as we should, as I showed a couple of slides ago, then we actually should get something close to this average value, which is based on those paths which are inside the network. So, by doing that, we get our final result, which is shown here. At the bottom of this table, you can see average value, which is 232, and then you can see those corrected values, those integrals that take into account crossing of the interface, which are now about, which are certainly less than 2.5% in difference. Now, for 2.5% of error, we can always think as a computational error. But before this correction, it was almost 10%, which is certainly not just for computational reasons. So, in this way, we proved 2 things. Of course, theory was right. It is sound theory. There is a difference. There is an error if we just measure integral of this outer path. But on the other hand side, from engineering point of view, from practical point of view, it's not a big deal. It's less than 9% in this case. And it is so for all welded joints which do not have big difference between their regions, between weld metal, base metal, and heat effective zone. So by doing that, we also prove that this direct measurement technique, which is shown here, is a valid experimental technique to measure J integral. And this is very interesting way to experimentally evaluate J integral, and to be honest, I'm surprised that it has not been used more often. Now, the point here is that, let's say, tensile specimen, as shown here, we can use to measure strains along points from here to B, and then from C to D. This is what is available. Those are outer surfaces. And interestingly enough, if we express J integral in its terms, we find out that those strains measured, once again, along this path and along this, of course I'm using symmetry, so not all the way, just half of it, are enough. Of course, also in combination with crack mouth opening displacement, which we definitely also need to measure, and which is relatively simple in addition to strain gauges. So we can reduce J integral to measurement of strain strain gauges and CMOD. At that time, when this was a bit popular, it was done by strain gauges, of course. Nowadays, this can be done with digital image correlation, but surprisingly, nobody is doing it. Well, maybe people will go back to this excellent experimental technique, because in this case we are, as it says, directly measure J integral. We don't need all this stuff to prove that what we are really measuring is really a measure of J integral, as in the case of standard experimental evaluation. So what J is physically here represented with are these strains. You can see some real measurement here. This is on the back side, uncracked side, and here there is a cracked side. So difference between these strains is actually J integral. This technique was also applied decades ago to a pressure vessel. And what is the point here actually? When we want to check if a pressure vessel, if a cracked pressure vessel can sustain certain pressure, we can, of course, apply crack driving forces, which is a matter of calculation, and JR curves, which is a matter of standard testing. We can compare them and see what will be the critical pressure. And I will show you later on how it looks like. But we can also do something more direct. We can measure J integral on the pressure vessel if we apply this special if we apply this modification of direct measurement of J integral. It is relatively complicated, and not surprisingly that people are not often doing it, but what we did in these experimental investigations decades ago was to cut out one piece of the pressure vessel containing weldment, then make artificial crack in that piece, and then weld it back to the pressure vessel. I forgot to mention, while we had it in our hands, we instrumented it with strain gauges. And then there was a special design how to do that, so that those strain gauges inside the pressure vessel really work. It's not simple, but we were successful in doing so. And you can see here at the bottom, M is representing strain gauge, and of course crack multiple displacement was another parameter that we needed. So this is valid only for the outer cracks. For the inner cracks we can't do it. And here is the path of measurement. And what we also did is to evaluate the effect of biaxial stress state, because it's not the same as uniaxial, but it turned out that the difference is just 2%. You can see it at the bottom of this left column, that actually this criteria for yield strain is just 2% lower than in uniaxial stress state. But this biaxial stress state is for cylindrical shape, and in the case of spherical shape, and spherical pressure vessels are a bit more critical, difference is significant. So once again, good knowing of what is behind the story enables us either to neglect something or to be sure that we have to take it into account. Also, stress strain curve, which is shown to the left, in this case is represented by linear, it's simplified better to say by linear curve, two linear parts, which is good enough representation if plasticity is not too much expressed. And it's a better representation of material behavior than just elastic, ideally plastic, as was done previously. So these two small corrections were applied to get a better result. Later on I will show you also. Yes?
I have a question.
Yes.
If it's an internal crack, how do you define the parameter for this one? Is it still valid for the fracture mechanics?
Yes.
Or we have to think differently, like because of the thickness, we can calculate the failure.
I'm not sure I understood.
Okay.
Maybe we can discuss it later. I heard, but I didn't understand.
Okay.
We can discuss it later. So maybe a comment that we maybe I missed to say that we made I didn't say made artificial crack in this cutout piece, and when we put it back, we had the pressure vessel with a crack, and then in a cross section, which is actually shown here on the bottom to the right, we had a bit simplified but relevant case for analysis. Now, as you may have noticed, we actually reduce in this direct measurement technique, we actually reduce J integral to the area between strains measured at the cracked and uncracked side. What is here in the So a few comments about what I just explained. If we take as a relevant way to evaluate critical pressure, we can compare these crack driving forces as shown to the left. You can see them here, positioned at the crack depth, which is 60% of the thickness, or here when it is 35%, or here when it is 20%. We just tested different cases. And at the point where crack driving forces are intersecting with JR curves, we can establish a critical point. In this case, it is defined as approximately 0.83, I would say, which is just a parameter indicating critical pressure. It is about 83% of pressure that would correspond to yield strength. So I would say it's surprisingly high value. We are dealing with 60% of crack length, crack depth. We are analyzing the problem of crack grow through the thickness. And in some other cases, it's even higher. In these three cases, we don't have any critical pressure. This pressure vessel can sustain pressure that would cause stress equal to yield stress, and still crack will be stable. It will not grow. Now, in this case, we can also ask ourselves what the direct measurement of J integral physically means, because it is just one point that we are going to get at a certain pressure level. And our conclusion is that by direct measurement, we don't need crack driving forces and we don't need JR curves. We are just measuring pressure vessel as it is. And when it breaks, that will be the critical pressure, and we will record it by direct measurement of J integrals. So that was a kind of explanation and introduction to. Now I have to solve another mystery why this slide is not showing. Well, it's not that important if others will show that's good enough. What this slide shows are thicknesses that were calculated according to the standards, which indicates that in the case of this high yield strength steel, we still needed slightly more than 50 millimeters of thickness. Now the producer could not satisfy that condition. He would make 47 millimeters, and the decision was to still follow this line of thinking and this design, and to reduce so-called safety factors. That is, from the engineering and philosophical point of view, really important further discussion. So I will use a couple of minutes. Safety factor actually covers what we don't take into consideration or what we don't know about our material and our construction. So if we know precisely how material will behave in the presence of cracks, if we know how the structure will behave, then we can certainly reduce safety factor. We can, at the extreme case, make a design without safety factor, but that's unreasonable. On the other hand side, using safety factors like 2 point something is also not very reasonable and rational in this situation when we can make extensive experimental testing and other analysis to prove our case, to prove so-called fitness for purpose. And I will show you how this was done. Supposedly the next slide is working. Okay, so this is the prototype. We call it the prototype. Three of them were made, 2 of them were tested, and that was really something new at that time, and still does not, you will not find many more examples of approach like this. So the most stressed part of a pipeline is the one where there is a 5-degree knee at the bottom, of course, because at the bottom of the pipeline there is a hydraulic pressure, the largest hydraulic pressure. So, this so-called prototype was made in the real dimension. We call it also real scale prototype. You can see it here, and you can see a couple of these LS, LM, and so on. Those are welded joints. They're made different welding processes. We are not interested in that. This is what made stress concentration. This is the cross section. You can see these 47 millimeters. You can see manual arc welding and submerged arc welding as 2 processes used, and you can see this cross section as well. Now, this part. Sorry. Next slide. This is the critical part of the prototype, and here you can see strain gauges, crack opening specific gauge, and you can see a couple of artificial cracks, so that we could follow the behavior of the material and structure at the same time. Now once again I have the same problem, that I only see part of the slide, that you can only see part of the slide. So I will improvise once again. Those are these artificial cracks. You can see them. Okay, I'm getting it. So you can see some basic data. explained and written, as I already told you. And this is important, how testing was done. So it was hydrostatic testing, which was done in 3 phases. First was just to check the measuring system. Then the second one was to load the prototype up to work stress level. That was up to 9 megapascals, 19 bars. And then to overload the prototype by 30%. And that third step produced some surprising results, but still we could prove fitting for surface. That was purpose, sorry. Some results are shown here, but once again. So these are the results for material testing. Just please pay attention to the yield strengths in welded joints. You can see even higher values that I mentioned, because base metal is about 700. So this is so-called overmatched welded joint, which was another, how to say, brave decision to make. Because typically we would make over matching welded joints with common steel, but with microalloyed high-strength steel, actual philosophy is better to use undermatched welded joints. But in this case we couldn't because of design requests, and yet it was okay at the end. You can see also here a photo from 1976 in Simonopoulos, as I told you, and this here is the prototype. So these people participated actively to this story, and this one here is my father. He was also the father of fracture mechanics in Southeast Europe, and mostly because he had this chance to make such experiment as this one. Now you can see strain gauge distributions and testing what on this developed in 2D space mantle. You can see that strain gauges were positioned mostly along welded joints, because we had 2 problems here from design point of view. One was this 5 degrees D, which was some stress concentration, and the other was undermatching, overmatching, whatever, matching between weld metal, base metal, and not to mention heat affected zone. So all these facts actually led to the unusual behavior, which I will show you at once. And you can see it here. If you look at the strain gauge 53, you can see that this is pressure, this is strain. So strain follows the pressure, linear elastic, first stage, second stage, third stage, unloading, everything fine, as expected. Linear elastic behavior, also completely benign, almost for number 3, but with strain gauge number 2, which is one of the welded joint, you can see some non-linearity, and you can see that after unloading there are some plastic strain left. Even that is not so strange as the behavior of strain gauge number 34, which goes this way first stage, then second stage, and then very strangely it goes this way. So not only that there is a plastic strain here, something strange has happened in elastic region. Probably some large elastic strains appeared because of this facts that I mentioned, stress concentration and different ratios between yield strengths of low metal and base metal. But this is just a lecture, not a scientific presentation. I will not try now to explain why it is so. I just wanted you to notice that in a relatively simple experiment, in relatively simple structure and relatively simple material, we still got some quite interesting behavior. Anyhow, we did later on, we did some numerical calculations because in 1976 that was not possible. Later on we made these nice colored figures. You can see boundary conditions. You can see here how this model deformed. Of course, this is exaggerated view. And we have actually tried to simulate this strange behavior, and to some extent we were successful, but few facts are still to be uncovered. So I'm just showing you these nice figures that you can see. I'm not showing only the history of fracture mechanics, but something that has been done recently. And we, as I told you, did get this plastic strain at the end. Of course, point is that according to theory, we should have not had any plastic strains. But once again, due to stress concentration and mismatching, we actually did get plastic strain. This is one very important and a bit worrying factor. But the other factor was, the other most important factor and conclusion was that this prototype still behaved well from the structural integrity point of view. Those artificial cracks did not start to grow. So even under very high loading and cracks with relatively large dimensions, it was safe. Here are presented some few more details. And this is numerical simulation of that strange behavior that I mentioned. You can see that we almost did get the same behavior, which was not simple. We had to put some initial deformation, some initial stresses, and so on. And also a few other results in that respect. We can go faster now because we still have the third part of my lecture on the agenda. I think by this we covered the second one. Just to go.
Sir, I have a question for you.
Results?
I
Yes.
have a question. You told that you tested 2 prototypes out of 3.
Yes.
Did you get the same strain behavior for the both? Or
No,
it was just once?
no, because the one was not tested, and the third one was tested, but in a different way. It was tested by explosion.
Okay.
The idea was to check what would be impact of eventual water hammer,
Okay, yeah.
and even that showed good behavior.
Hmm.
It's a good question. Okay. Now, to conclude the second part, we still have a few slides. I ran through these results which I didn't want to analyze, which were more or less corresponding to the experimental ones. And now, finally, what we also did here was structural integrity analysis or fitness for purpose analysis based on drag driving forces and JR curves. The concept is shown here and already explained. As for the drag driving forces At that time, this is early 80s, we couldn't use finite element method, but we rather used a model proposed by Radvani, Erdogan, and Irwin, which really produces very good results for cylindrical pressure vessel. It correlates J integral in the displacements and strains, and using it we can produce these drag driving forces here, just schematically shown from 1 to 5. I will show them later on. Now just let me show you how JR curves were experimentally evaluated. At the top, you see 3-point bending specimens, and at the bottom, you can see tensile panels. It's very important that I explain now. We use this standard form of testing, but this is over-conservative for pressure vessels. Pressure vessels are in membrane state, stress state, and for them, tensile panels are surely more relevant, but they are not according to standard. So we did both. And we got different JR curves. You can see them here. Of course, those obtained by tensile panels were closer to reality, and those obtained by 3-point bending were more conservative, which is not a bad thing to have, especially once our approach was not very conservative one, as I explained at the beginning. So this is the result. Even with conservative approach, even with the crack, which is about half of the depth, we still need 85% of pressure to get to the critical state. And design pressure is about half that value. So in this way we proved numerically, analytically, experimentally, whatever, that design was safe. But you can see that it is very, very complex investigation. It was necessary because it was done for the first time under circumstances that I explained. This is not relevant, so now we go to the third part. I need some help. Hello. Third one, please. Yes.
How do you propagate the initial flow of the 3-1 demonstrators? What are the tests? Yes, yes.
And now something completely different. Micromechanical modeling, what I will present, was done in the scope of doctoral thesis. It was a student from Libya, and he did excellent job, one of the best students ever. I will show you, after a short introduction, some basic facts about ductile fracture as presented in scope of micromechanical modeling, and then I will explain what is the local approach to ductile fracture, what is the person and complete person model, and then I will show you some results. So what we are doing here is how to use results obtained on specimens on a real structure. So it's not completely new, because I already mentioned that problem, which is of course always present in our practical life. This whole approach, which is either called local approach or micromechanical modeling, was initiated by this need to know what is the difference between behavior of crack in a specimen and crack in a real structure. I just mentioned that crack in a 3-point bending specimen would behave differently than crack in a pressure vessel or in tensile panel, and these differences are not small. So this micromechanical modeling is one way to reduce unnecessary conservatism in our approach. Well, whatever it is, as you will see, it was once again initiated and inspired by Rice. Jim Rice and his student Tracy made the first model, which was about void growth. In their case, it was just an isolated void in a remote uniform stress field. Later on, it was improved, modified by a group from France called Beremin, and then by a bit different approach, so-called coupled approaches, including the person model, then modified by Vergaard and Needleman, and finally, in a way, as far as I'm concerned, completed by Julian Schenk. He will be at the conference right away, and his contribution to this field is really huge. So this is schematic representation of micromechanical modeling, or in this case, mechanism of ductile fracture. Pay attention to inclusions, which are here in black, which are relatively big. Those are primary inclusions, or these smaller, which are secondary. And around this inclusion, voids start to nucleate, and then they grow, and then they would coalescence at some critical event, and this is how crack actually is, stable crack growth can be described. You can see it also here. If there is already a crack, you can see some inclusions here, then voids, and then their growth and their coalescence. And that can be described in the scope of continuum mechanics by so-called person model and its modifications. So here we have a term which is actually from Mises' yield criterion, and some other terms that try to incorporate material behavior after it gets into plasticity. Once again, we are not dealing with details here, but just pay attention to this volume fraction. This is very important parameter, this F, and there are many versions of that parameter that I will mention for some details that you will see soon. So here, the next slide, we can see that volume fraction consists of two parts, nucleation and growth. You can see also some micrographs indicating, once again, these primary or secondary voids, that is also important to distinguish. You can see also this parameter A, defined by Joe and Needleman, with few material parameters. And just to notice that primary voids form around non-metallic inclusions like sulfides, oxides, silicates, whereas secondary voids, in the case of steel, would form around iron carbides. I'm emphasizing this because they are a bit different, and in some cases these secondary voids can be neglected, but not in the case of steel, with at least a couple of hundreds of percent of carbon, which is big, or better to say inadditive. This so-called Gerson Vergar-Liederman GTN model is a bit more complicated than original Gerson model because it doesn't take into account just F as a void fraction, but also it distinguishes two values, one before getting critical value and the other after getting it. It is something like a stress strain curve, so linear elasticity before we get to yield strength and then afterwards different behavior. And taking into account modifications like this, we can better describe behavior as shown here in terms of diagram force versus reduction of diameter for tensile testing of round specimens, as is done typically to simulate micromechanical modeling. You can see a difference if you take into account this critical value or if you don't take into account. The whole story is actually about how to model material behavior, how to get from some microstructure parameters to be able to simulate crack growth, ductile crack growth in a material, to simulate it numerically. That is a very difficult task, and it is impossible, of course, without material parameters. But here there is an explanation how we use material parameters which we can measure to get this numerical simulation of material behavior. So we would need initial void flow fraction. This is a relatively simple task. It is done by microstructural analysis. And then we would need some other parameters which are also related to volume fractions, void volume fractions. You can see how this is done using microscopy. But at this point also let me emphasize another parameter which is actually not in this scope, but it turned out to be an essential one, and that is a lambda. Lambda is a mean distance between inclusions. It was found out once people started to numerically simulate micromechanical behavior, that numerical simulation was typically the finite element method, and now there is the same. They found out that they need lambda parameter because finite element mesh has to be designed according to the value of this parameter. I would say that this is a bit of a weak point of this whole story, still unresolved. You will see some strange results in a term of this parameter, but once again, as in the case of crack tip open displacement, we use it and don't excuse it because it works. And of course, there are younger generation, they should get a deeper insight why is this so. I will be back with this lambda story. Just to go briefly through standard way how we use quantitative microstructural analysis. Is there an inherent way or what is this generally? We will not get into details, but there are slices that we measure this distance between inclusions, and then by certain, a bit complicated but not too complicated technique, we can evaluate mean free path between inclusions, as is the official name of lambda. So this is it. You can see how it looks like with real micro graph, and we can now go on with micromechanical modeling. As I already showed, the most recent development was done by Julien Jean. It's already 20 years, but after that we didn't have any more development. So this is something that is once we try to apply something obtained on specimens to real structure. So in this investigation, we used once again two different kinds of specimens: flat, smooth tensor panels and single-edge notch pin specimens, which are practically 3-point bending, as was previous case. You can see this micro alloyed high-strength steel, not as high as in the previous case, but something that we often use for pressure vessels. You can see basic data about chemical composition. What is here marked in red is strange data that we obtained from the producer, who claimed that there is sulfur as high as 0.16, which is probably wrong. That's still to be checked. It probably should be 0.016, but even that is relatively high value. You can see also that phosphorus is relatively high in pure metal, and that is relevant to interpret results that we obtained at the end of this testing. Now here you can see those parameters that we need for calculation. They were determined for heat affected zone. We're not sure which of these two subzones, so we put them together, and weld metal. Because we tested and analyzed two different cases, one where the crack is in the weld metal, the other one is in a heat affected zone. Those are just basic data about the welding. We're not much interested in that. Here is how testing was done, how the specimens were cut out, different types of specimens as explained, and what we used for person parameters. Here is how we determined mechanical properties. That's yet another story, but we don't have time to get into details. I will leave, of course, these slides with you, and I will also leave a couple of references so that you can, if you are interested, go in more details. It is very interesting how tensile properties are determined for the welded joint, so for weld metal, heat affected zone, and two actually of subzones, and base metal. As already mentioned previously, those are these four different zones with different tensile properties. Not too much different, but different enough to make to really get into analysis. So it is described here. It is done through a kind of iteration procedure, and I will show you just the final result. So it is combination of experimental and numerical effort to get something like this. We knew how it should look like, how it was really done, how it looked like in experiment, and then by iteration procedure, by adjusting the properties, we are getting this very close behavior to the real one. So in this way we were able to get true stress, true strain curves, which we needed for this analysis, and you can see them for base metal, coarse and fine grain, heat affected zone, and weld metal. After that was done, we could test both 3-point bending specimens and weld metal in two ways. Sorry, actually we tested the 3-point bending specimens and tensile panels, and then we numerically modeled them, of course. That's the point here. But 3-point bending specimens were simulated in 2D analysis, and tensile panels were simulated in 3D model. So that makes yet another difference. That was done intentionally to find out how it works in both cases. So here you can see also very important fact that finite element size were 0.2 times 0.2 in this specific case, which corresponded to lambda value for that or for well metal. So this is scrap in the well metal. In the case of heat affected zone, lambda was approximately 0.5 millimeters, so that was also the finite element size which we expected to work appropriately. And you will see here some results leading to the determination of the crack initiation point and leading to the J initiation values as shown here. So in the case of heat affected zone, our numerical simulation, micromechanical modeling, we got 121, and compared to the experimental results, 84, we thought it was good enough. In the case of well metal, it was even closer, 65 approximately, corresponding to 57. Since this was the first time that micromechanical modeling was applied to a welded joint, we were quite satisfied with these results. In the case of tensile panels, it's about the same story, but in 3D. So you can see now mesh in 3D. Once again, element size was tested in a way. We did make several different meshes, and one of them that is first here represented is according to lambda value. And once again, it is different for well metal and heat affected zone. You can see some details here. You can see once again how this void volume fraction correlates with J integral. You can see different behavior in the case of welded zone, well metal, sorry, and this is actually well metal and heat affected zone. You can see also distribution of volume void fraction, which is very similar to strain distribution. This is how we evaluated J initiation for tensile panels. Since it is not testing according to standard, we used stretch zone width to get 321 for heat affected zone and 125 for well metal. Now this really requires a bit of explanation. This is very surprising results. Heat affected zone should not be that higher than well metal. Actually, the secret is in this 0.016 and 0.013 content of sulfur and phosphorus, which really were very detrimental for well metal, and they did not affect heat affected zone, of course. So here is a complete list of comparison of numerical and experimental results. These are for 3-point bending specimens, and these are for tensile panels. Agreement is, I dare to say, or was better to say, surprisingly good. And now I am already 1 minute over the time. So I will really go fast, but this is important that you know this. If I would like to criticize this method, this micromechanical modeling, then I would have to use these slides. So here are experimental results for JR curve. And here are numerical results for JR curve if we use a mesh which is 0.2 by 0.2, which corresponds to lambda in the case of well metal. But then again, if we use mesh which is 0.5 times 0.5, we will get something, we get completely different. Of course, people using finite element would say this is because mesh is not fine. We are actually dealing with fine mesh with a good correspondence to experimental results, and then with rude mesh, which is completely wrong. But in the case of heat affected zone, we have almost perfect agreement between experimental results and the rude mesh. 0.5 times 0.5. Mesh that corresponds to lambda. And if we refine the mesh, we get something completely wrong. So there is a secret, just use lambda as to construct your mesh. And don't ask why, that is up to next generation to explain. So I think that would be enough for today. There are also a couple of other slides, you will have them at your disposal, and I just can conclude with the facts that I already emphasized. And this is that we can successfully apply this technique, this modeling, to welded joints, which is not simple, and that there is a problem with the size of ion elements. And I will conclude with this. So I hope I did not confuse too much, but at least if you are confused, it is on a higher level. Thank you.
Very interesting lecture. I don't know if anyone has one comment or question.
Yes, please. Sorry, I was looking at it.
Hi, thanks for the lecture. Do you have any comments on using J, which violate the fundamental principles, for example, in an initial stress or strain field or under non-proportional loading?
In all these cases, which would also include thermal stresses or volume forces, etc., we know how we should correct the original definition of J to get it back to the physical interpretation and valid energy release rate, as it was done here. It would not be line integral in that case, it would be a surface integral, but the story is basically the same.
Similar to what you do with the
Yeah.
welding.
Good question.
Okay, thank you. From this side, I think it's
From the left side, socialists.
Thank you. Just a question about lambda. What's the procedure to get this value?
I skipped over these slides, so you can check them. Basically, you get your micrographs, and then you draw lines, real lines, along the vertical, along couple of them, you measure the distance and then calculate the value. So that's simple.
Any other comment or question? Well, just over there, the last one.
Thank you. I'm just wondering if we didn't use the complete Gaussian model and we just used the normal one, are we going to receive the same, to get the same result, or what do you think?
No. We will get some differences, especially when we get deep into plasticity. Softening of material is differently described in complete Gaussian model, as I showed in one sketch, in comparison with the classical version of GTM model. But not a big difference, I have to say.
So do you suggest that we should no longer use the GTM model and use the complete one?
I suggest that one should use complete GTM model. It is, I dare to say it is superior model.
Thank you.
And of course you can ask that Jermaine Jean, please come to work.
For sure. Okay, well, it's time to finish. We thank you again, Professor Sedmak.